We've been talking a lot about the creation of the universe, but with inflation and with expansion, the question always comes up, how will it end? What will happen to the end of the universe? Well, it's going to depend upon the geometry of the universe. First off, is the universe open, closed, or flat? Open meaning it's going to expand forever. Closed meaning it's going to expand, turn around, slow down, and come back in a big crunch. Or flat meaning that it will expand and then eventually the expansion is going to stop. The moment all of our observations kind of indicate that a flat universe is most probable. It will keep expanding until a certain point, and then it will just stop expanding anymore. How the universe will end is also going to be determined by how much dark matter there is. Dark matter has a huge force of gravity. It attracts matter closer and closer together. We don't know a lot about dark matter yet. It's a very new thing in our knowledge base. As we have a better theory of dark matter, we will have a better theory about how the universe will end. The other one is dark energy, how much dark energy there is, because dark matter pulls, dark energy pushes, and is expanding and accelerating that rate of expansion. So it's a huge question mark at the moment. None of us are going to be around to see the end. Hopefully it's going to be a long, billions of years in the future. But that is a huge question that's still remaining out there. All right. So what actually caused the Big Bang? As we try and figure out that, one of the things that we're trying to look at is something which is called unified field theories. And as we get this in physics more finely tuned, we'll have a better idea of what the origins of our universe looked like. Now, unified field theories states that there are 4 fundamental forces that control everything, absolutely everything that you and I see in our normal everyday life. These 4 forces are called electromagnetism, the weak nuclear force, the strong nuclear force, and gravity. And a lot of cutting-edge physics right now is going into trying to understand these 4 forces. So let's take a couple minutes and talk about each one of these in turn. The force of gravity, you understand. The force of gravity is what holds everything together. And we're going to spend a few minutes on each of these. The electromagnetic force, this is responsible for all of chemistry. The strong nuclear force, that and the weak nuclear force only occur inside the nuclei of atoms. But I would definitely put a little star by this. These are the 4 forces that scientists can use to explain absolutely anything that they see at this point in time in any of their observations. So gravity. The best understanding we have of gravity right now is that when you have matter, the presence of matter causes space itself to curve, creating these lovely gravity wells that we described when we were talking about black holes. Gravity is always attractive. We've never ever seen repulsive gravity. We don't have any idea that it should exist. But it always causes there to be holes or dips in space-time. And objects have a tendency to fall down these ridges or dips. The range of gravity is infinite. The Milky Way galaxy and the Andromeda galaxy are many light years away, and yet they are gravitationally bound and attracted to each other to such an extent that we are colliding with the Andromeda galaxy. Of the 4 forces that we know of, gravity is the weakest. It is much weaker than any of the others. And I'll give you some examples in the next slide. It is predicted that each one of these 4 forces has a particle that transmits the force, and the predicted particle is one called a graviton. Sounds like a ride at an amusement park, but at the moment this is a theoretical particle, and at the moment I'm making this video, this particle has not been found yet. So if they find it in the next little bit, well, before you listen to it, cool. But at the moment, it's still a theoretical particle. The next one of the four fundamental forces is electromagnetism. This is kind of the one that you and I experience. Our bodies are wired to really interact with electromagnetism. Electromagnetism is responsible for all chemistry. Well, chemistry is what makes up DNA and what makes up atoms and what makes up cells and respiration and food digestion and all of that. There would be no life without electromagnetism. Electromagnetism, simply stated, is that like charges are going to repel and unlike charges attract. That's the simplest way of stating electromagnetism. But electromagnetism, because of the fact that this attraction and repulsion comes into play to how atoms are actually held together when you make a molecule. This is responsible for the structure of all matter. You, me, and cars are all held together by electromagnetism. Now, electricity and magnetism can both be attractive and repulsive. It's different than gravity. Gravity is only attractive. But electricity, you can have things that are attracted and you can have things that are repulsed. Very different force. The particle that transmits this electromagnetic force is the photon. You're familiar with photons. A little wave-like length of light is a photon, but it also has a particle nature to it. And that wave particle nature of photons is woven into the subject called quantum mechanics. Complicated and really kind of nifty. Electromagnetism is 1 × 10⁻39 times stronger than gravity. Let me give you an example. You are gravitationally attracted by the force of gravity to the ground. Now, why don't you just go being pulled from the surface of the earth right down to the center of the earth by this huge, strong force of gravity? Well, the thing that keeps you from going through the earth is electromagnetism. And the reason is the bottom of your feet. There's the bottom of your feet. There's a foot. There's another foot. The bottom of your feet are made of atoms. And every single atom has a positive nucleus, and the outside edge of the atom is full of electrons. That means the bottom of your feet are negatively charged. Now you are standing on the ground, and ground is made out of atoms. Every single atom has got a positive nucleus and a negative outside edge. So what is actually keeping you from falling through the ground? The bottom of your feet are negative due to electrons, and the ground itself is negative due to electrons. So you are actually hovering above the ground because of the fact that like particles repel each other. So you're not falling through the earth because of the electromagnetic force. If gravity was stronger than electromagnetism, oh boy howdy, you would go straight through the ground and we would all be squished together right at the core of the earth. But that electromagnetism holds up your body and makes you have structure. The next one of the 4 fundamental forces is called the strong nuclear force. Now, it is the strongest of the 4 forces. Yay! Here's how the strong nuclear force, how I think about it. If you think about the nucleus of an atom, the nucleus of an atom is made of lots and lots and lots of protons and neutrons. Well, protons are all positively charged. And positively charged things should repel each other. Well, 100 years or so ago, scientists looked at that and said, well, that's curious. Why in the world would all these positively charged things be able to be held really close together in a nucleus when they should repel? We know like charges repel. They said there must be another force that is really, really, really strong, that is stronger than the electric force of repulsion, and that stronger force that holds the nucleus together, they called the strong force. Okay, maybe not the most creative name, but it works and it helps me remember it. The strong force is really strong, but it has a very short distance over which it acts. Outside the nuclei of an atom, and you and I are never going to really see smaller than the nuclei of an atom unless you have really cool scientific toys, we're not going to experience the strong nuclear force. It's doing its job holding the nuclei in your body together. It's also responsible for fission and fusion. If you remember back when we talked about fission and fusion, if you've got 2 little atoms that are hydrogen and a hydrogen, and you fuse those together to make a helium atom. In the process of doing that, some of the strong force is actually transformed into an extra little bit of energy, and that's the energy of nuclear fusion that powers our stars. The strong force is always attractive, kind of like gravity. There's not a repulsive strong force that we've ever found. And there is a particle of transmission, and they called it the gluon. Why did they call it a gluon? Because it is the world's strongest glue. Yeah, bad pun, but that's why they named it that. The fourth fundamental force is called the weak nuclear force. And it is weak, but gravity is weaker. So it gets a little tricky. It is not the weakest. Gravity is the weakest of all of the forces. What the weak nuclear force does is it helps hold the neutrons and neutrinos together. If you recall, a neutron is really a proton and an electron that have been kind of bonded, and what holds them together to make a neutron? This weak nuclear force. The particles that transmit this force are called W and Z particles. It's a very short range, again, within the nucleus, and it's responsible for some forms of radioactive decay. And if you've ever had any physics or nuclear chemistry, this gets involved in beta decay, because beta decay is when a neutron decomposes into a proton and an electron. It's very weak, many times weaker than electromagnetism, but not as weak as gravity. Gravity's the weak dude. All right, that is going to finish this bit, and we're going to continue next time talking about how do scientists unify all of these into one single force.